A uniform wire ABC is bent at right angles at B. When it is suspended from B, the parts AB and BC make angles of 30 degrees and 60 degrees respectively with the vertical. If the mass per unit length of the wire is m and AB is h times BC, find the value of h. Let's look at the mass of BC. Well, the mass per unit length, that means per meter, is m. So if we have BC meters, okay, then the mass of BC meters is BC times m. Okay, 1 meter has a mass of m, so BC meters will have a mass of BC times m. Now what about the mass of AB? Well, AB is just h times BC. Okay, it's a multiple, some unknown multiple h of BC. So we multiply its length by the mass of 1 meter, which is m. So we get h times BC times m. So now we can look at the force on AB. It's uniform, okay, so we can treat this part of it as if its mass is concentrated at its center of gravity, which is the midpoint of AB. So we multiply its mass, h times BC, by m by g to get its weight. Similarly over here, we multiply the mass, which is BC times m times g, to get the weight of this part. This is the center of gravity, the midpoint of BC. Okay, the system is in equilibrium, so the sum of the moments of the forces on the system about any point is 0. So we choose the point B. Now why do we choose the point B? Because, well, we have a force at B. Because this wire is suspended at B, so the moment of this force about the point B will be 0, of course. So this is obviously the best point to take moments about. So we only have to consider these two forces. So the moment of these two forces about the point B, the sum of the moments of these two forces about the point B must be 0 for equilibrium. So this force here has an anti-clockwise moment about the point B, whereas this force here has a clockwise moment about the point B. So the anti-clockwise moment due to this force must equal the clockwise moment due to this force here. Okay, so we need the perpendicular distance of B to the line of action of this force. We could also show this distance here. Okay, this is 30 degrees. I'll just write it in here again. So we have to multiply this distance by the sine of 30 degrees to get the side that's opposite 30 degrees. Well, this distance is just half of AB, which is half of h times BC. Okay, so it's half of AB, but we are given that AB is h times BC. So we multiply this distance, the hypotenuse of this right triangle, by the sine of 30 degrees. So that's what we have here. Okay, so that gives us the distance of B to the line of action of this force. And we multiply that by the magnitude of the force, which is this thing here, m. Well, it's written slightly differently here. Okay, so that's the moment of this force, and it must equal the anti-clockwise moment, or sorry, the clockwise moment due to this force here. So to find the perpendicular distance of B to the line of action of this force, that's this distance here, which we can show here, we need to multiply this distance, which is half of BC, times the sine of 60 to get the side opposite 60 degrees. So half BC sine 60 multiplied by the magnitude of this force, which is mg BC, or BC mg. So we have a lot of cancelling going on here, obviously. We end up with h squared sine 30 equals sine 60. The sine of 30 is a half, the sine of 60 is root 3 over 2. Multiply both sides by 2 and take the square root of the right hand side. So h is the square root of 3, which is 1.316. So that's what we need to multiply BC by to get AB. So AB is 1.316 times the length of BC. Two rough rings of equal weight W are a distance d apart on a horizontal rod. A light, smooth, inelastic string of length 2L connects the rings. Another ring of weight 2W slides on the string. The coefficient of friction between the rough rings and the rod is mu. Show that the system remains at rest if D is less than this quantity here. So this ring has weight W and the string is pulling on the ring. Let's call that force T. It's directed away from the ring and along the string. Now there's a contact force between the ring and the horizontal rod that's perpendicular to the surface of contact. So the force on the ring due to the rod is upwards. We call this R1. Now both rings are rough, so what's going to happen here is that the ring will want to move towards the right, so it will exert a force on the rod, which I will indicate in blue, in the horizontal direction, okay, because the rod is rough. Okay, this blue vector is the force on the rod due to the ring. Now, if the ring was smooth, then the ring would just glide over the rod and exert no horizontal force on the rod. But because the ring is rough, it kind of digs into the rod and pushes on the rod in this direction, in the direction that the ring wants to move in, of course, because we have a weight attached here. Okay, so now we just apply Newton's third law. So if the ring exerts a force on the rod in the horizontal direction, the rod is going to exert an opposite force on the ring. So this is the friction force which opposes the motion of the ring. Now let's suppose that this ring is on the verge of moving, so it hasn't moved yet. So the maximum friction force is applying here. So that depends on mu, the materials that the ring and rod are made out of, how rough the surfaces are, and this normal force R1. So the rings are on the verge of slipping. Remember, the friction force goes from 0 up to a maximum given by mu times the normal force. So I can write F for the friction force. Okay. If the system is on the verge of slipping, then the ring is basically exerting the maximum amount of force on the horizontal rod that it can exert. And by Newton's third law, we have an equal and opposite force acting on the ring due to the rod, and that maximum force is mu times the normal force R1. Mu times the normal contact force. Now for the second ring we have a very similar situation. Let's call the contact force on the second ring due to the rod R2, which acts perpendicular to or normal to the surface of contact. This ring is going to push on the rod in this direction, so by Newton's third law the rod exerts a force equal but opposite on the ring. Okay, so it's going to be mu times R2. Same mu as over here, same rings, same horizontal rod. The weight of each of these rings is W. The weight of this ring here is 2W. The string has length 2L, so we can see it's each side of this triangle must be 1L. Okay, so we will assume that the system is on the verge of slipping. It hasn't slipped yet, so equilibrium conditions apply. Let's suppose that the angle between the vertical and this string here is theta. Now by symmetry, this angle over here is also theta. Okay, this is an isosceles triangle. So both of these angles are the same, so the angles next to them are the same. Let's look at the forces on this ring here. So that's what we have over here. So we resolve these two forces in the vertical direction. So if this angle is theta, so is this one here. These are a pair of z angles. So the component of t in the vertical direction is t cos theta. And the component of this force is in the vertical direction is also t cos theta. So we have t cos theta plus another t cos theta. So that's 2t cos theta. Okay, and that must equal 2W for this ring to be in equilibrium. So we get t cos theta equals W. Now let's look at the vertical components of the forces acting on this ring. The vertical components must sum to 0, okay, because this ring does not move in the vertical direction. It only moves in the horizontal direction. So the forces up are R1. That's the only force up. What about the forces down? Well, we have W vertically down, and we have the component of this force in a in the vertical direction. Okay, we want the vertical component of this tension force. So we multiply T by cos theta. So T cos theta plus W. But we already have that T cos theta is equal to W, so we can plug it in here to get R1 equals 2W. So now we have found R1 in terms of W. Now we can take the moments of any part of this system about any point, and we will get 0 because the system is in equilibrium. The sum of the moments will be 0. So we will take the part of the system that we are familiar with. Okay, we are not familiar with this part over here. We haven't found R2. We have R1 in terms of W. So this part of the system consists of not just the string, of course, but this ring here and this ring up here. The string actually has no mass, so the system really just consists of these two rings. Okay, the subsystem, I should say, that we will use to take moments of. Okay, we will take moments about the point A, so that will eliminate the tension forces. The moment of the tension forces on both rings about the point A will be 0, because the line of action of these two tension forces passes through the point A. Also, the moment of this tension force and the 2W force about the point A will be 0. So, in this part of the system indicated in purple, only 3 forces will have moments about the point A. This force R1, the force W, the weight of the ring, and the friction force on the ring, mu times R1. So we take the moments of these 3 forces about the point A. Now R1 has a clockwise moment about the point A. These 2 forces have anti-clockwise moments about the point A. So here's the clockwise moment. So we have to get the perpendicular distance of A to the line of action of R1. Well, that's just half of D over 2. So we multiply R1 by D over 2. Now, what about W? Well, to get its moment, we multiply W by this distance, the same distance as before, D over 2. Okay, W has an anti-clockwise turning moment about the point A. And finally, we have mu R1. So the line of action of mu R1 is this line here. So we want to find this distance here. Now we want to get this distance in terms of what we're given. Okay, L is the length, half the length of the string. That's the hypotenuse of this right angle triangle, and the distance from here to here is half of D. That's D over 2. So to get this distance here, we have to get the square root of the hypotenuse squared minus this short side squared. D over 2 squared is D squared over 4. So that's what we have here. So we multiply the magnitude of this force, mu R1, times this quantity. Of course, we don't want R1 to appear in our answer. If we just have a quick look at the answer, we can see that R1 obviously doesn't appear in it. Mu and L appear in the answer. So we just go back up here and write R1 in terms of W. And if we do that, you can see that all the W's disappear. That's exactly what we want. So we just have an equation involving D and L. On the left hand side here, we just have D, and we subtract D over 2. So we D minus a half D, that's a half D. We get a half D on the left hand side. And we have 2 mu into root L squared minus D squared over 4. All we do next is multiply both sides by 2 to get D equals 4 mu into root L squared minus D squared over 4. Now we want D, the distance between the rings, in terms of mu and L. So we just have to make D the subject of this, just square both sides of it. So you get a 16 mu squared here multiplied by L squared, and a 16 mu squared by D squared over 4. That'll give you a minus 4 mu squared D squared. Bring this term over, factorize out D squared, and divide across by 1 plus 4 mu squared. Then you take the square root. So this is the distance between the rings when the rings are on the verge of slipping. So this means that if the rings are any further apart than this quantity, then they will slip towards each other. If the distance between the rings is less than this quantity here, then the rings will remain at rest. Intuitively, that makes sense.